Welcome to Consistently Hashing with Gaurav.
Hello. In today's video, we will be talking about the recent blog that the OpenAI team released on how their Postgres clusters handles 800 million ChatGPT users. So I have the blog with me. So let's yeah. So this is the blog scaling Postgres to power 800 million ChatGPT users. In this video, what we will do is we will go to the items that has been listed here. We'll try to identify what's the current scenario, what did they do to fix that scenario, and what can be done in the future to ensure that it scales even better, right? So yeah, so let's start. Okay, so for years, Postgres has been one of the most critical under the hood. Okay, so this is fair. And yeah, over the past year, our Postgres load has grown by more than 10x. And this is a tremendous number. So 800 million ChatGPT users, I think it's one of those apps which, scaled rapidly with the rise of AI. And even if you decrease the scale by 10x, right? So it was still having to support 80 million ChatGPT users, and now the scale that load has grown even more. It has grown by 10x. Considering all the different or considering the amount of increase in their population and also the different features that they have released, right? So it's difficult to it's and this is one of the fundamental principles that developers have to understand when they are designing an infrastructure. You cannot design scalable infrastructure from day zero because the amount of if you because if you try to do that, if you try to build infrastructure which can support, let's say, 1 million users or 100 million users, right, from day one, you will never be able to release your app, right? Because there is a lot of pain, a lot of planning that you have to do to kind of get to that level of scale. You have to understand the operational side of it as well. So the very fact that ChatGPT or OpenAI has been able to function successfully without much noticeable downtime for this longer duration is pretty commendable, right? Moving on, Postgres can be scaled to reliably support much larger read-heavy workloads. So this tells us that they are more focused towards making the entire system read heavy, and it also tells us that they are not that much worried about the writes and they're more worried about the reads. So this is a critical point to note here, and this will answer a lot of criticism that this article has faced from the database community. So they say that they use a single primary Azure Postgres instance and nearly 50 read replicas spread over multiple regions globally. Okay, so this is another important point. They have a single primary Azure server instance and nearly 50 read replicas. How Postgres operates is that what this means is that you have a primary instance and then you have multiple read replicas, which are basically replicating data from that specific primary instance. So the problem with having a single primary instance is that in Postgres, your writes can happen only to your primary instance, right? So that means that a single instance is susceptible to failure. And if that specific instance goes down, then you can have a lot of then your system cannot basically handle any more writes unless and until there's a secondary which can take over. Now, what read replicas means is that when your data is being written to your primary instance, it also gets written to your write ahead log. In most most databases have this in some form or the other. Now, this write ahead log or bin log or trans log or whatever they call it in different databases, this is basically this is read by the other read replica instances. It reads the data. It reads the data based on the last timestamp. And then it commits the data to its own Postgres instance, and that is how read replicas operate. It basically ensures that in a specific in a specific span of time, your read replica and your primary in a specific instance of time, your data which was written to the primary instance will be replicated to your read replica. Now, the time window between the read replica and the primary instance depends on a lot of things. It depends on which region to which region are you transferring the data from, because there are multiple concepts on there are multiple bottlenecks which kind of comes in when you are doing this kind of data transfer. You have the network infrastructure, you have the disk IOPS, and a lot of other things which also kind of comes in when you are talking about the time taken for data to be replicated between your primary and the read replicas. But we also need to, understand that there is going to be some kind of delay, and it's not very easy as well to kind of ensure the 50 read replicas have data up to date, almost real time, based on OpenAI scheme. So till now, I haven't seen any instance of. They do mention that they have 800 million users, and they say that they have to support millions of queries per second. But that does not tell us what is the total volume of data that they are transmitting. So we'll have to come to that point later. So we don't know what is the network bandwidth or the disk IOPS, or the number of or the volume of data that we have to write to disk, right? So these things are some things that we still have to uncover, and based on that, you can come up with a formula based on the region as well, based on the region or the location of the read replica and the primary instance, to understand how much time your total replication lag will take, right? Okay, so they are talking about why the initial design was not foolproof. So after the launch of ChatGPT, traffic grew, of course, and it worked well for quite some time. And okay, they saw multiple incidents which was caused by Postgres overload. This is a pretty common thing which happens in most companies. Your databases are the most resilient and also most prone to failure when traffic grows. And yeah, and yeah, so will databases are basically when your app is running fine, you don't care that much about the database, right? But when your app is not running well, your database is always the primary culprit. And it's also because it does a lot of work for you, right? So now, so they talk about a specific issue. An upstream issue causes sudden spike in database loads. True. Then widespread cache misses from a caching layer failure, a surge of expensive multi-way joins, saturating CPU, or a write storm from a new feature launch. These are all pretty common problems. Causes a sudden spike in database load. This can happen when we have an expensive query, which can affect other queries, other ongoing queries as well. So this is a very common noisy neighbor problem when you are running, because your workload is not isolated, and if a specific expensive query takes up most of the resources of your Postgres cluster, then even queries which don't have that much overhead can actually take up a lot of the resources. I mean, they become slow as well, and sometimes they also fail. Widespread cache misses. Uh, so I assume that they have a cache layer on top of Postgres, and so either they have Redis or Memcached sitting on top of their Postgres cluster, or they're talking about. I don't think they're talking about file system cache, but yeah. So I think they're talking about some other cache layer supported by Redis or Memcached, and when that layer fails, because cache is usually read only, right? When that layer fails, then the demand to answer the query falls upon the database, and because now your database has to answer more read queries, your the overall resource requirement kind of goes high. Cool. Uh, one very important problem with how expensive queries can affect the system is that if you have an expensive query, right, and it basically it creates a bottleneck in the execution of other queries, and because of that, what happens is the entire app becomes slow. So it's not a one-time problem. It's a prolonged problem where a lot of, as and when your expensive query comes, it kind of takes up the entire CPU or memory utilization of your Postgres instance, and the other queries are not serviceable. Cool. Yeah, this is the cache layer that they were talking about. They have expensive queries. I don't know why expensive queries. Okay, so they had a cache layer failure, which means the expensive queries goes into Postgres load. Request becomes slow. Yeah, this is a very common issue, right? And especially these three layers. I would talk about cache layer failure because I think it's more of a cache. You can have a cache if you can estimate how much data you're going to serve in the cache, right? So I don't accept. So cache is always supposed to be temporary. It's never a persistent. It's never going to be persistent, right? So I won't talk about cache layer because I look at cache as an add-on. But if your database itself is not partitioned or not laid out enough to answer certain important questions, I think that's a then adding a cache on top of that doesn't help at all, right? Expensive queries, I do sympathize. Write spike, yes, writes are important. I mean, write spikes are very critical failures of the system. But another thing that I want to point out here is that write spikes may also be because of the way that they are writing the data, or because of the data layout that they have in the system. Uh, Okay, they're talking about MVCC below, but we will get to that point. But uh, if you are writing to in Postgres, right? If you're trying to update a specific row multiple times, then you do get into lock contention errors, and I think this is what they're talking about when in the MVCC. But that means that the overall layout that they have in their Postgres database is not optimal. Or maybe it is because they could not avoid doing it, or they did not find a better way of doing it, or they did not want to add any more complexity by adding other databases, right? So write spike, I don't just attribute it to a surge in traffic. I think write spikes can also be an indication of a wrong data layout or a wrong database being used in the wrong circumstances. Okay, so moving on, although Postgres scales well for read-heavy workloads, we still encounter challenges during periods of high write traffic. This is largely due to Postgres' multi-version concurrency control implementation. I disagree with this completely. And this is exactly what I was mentioning in the previous section. For example, when a new query updates a tuple or even a single field, the entire row is copied to create a new version, and the heavy write loads. This results in significant write amplification. It also increases read amplification since queries must scan through multiple tuple versions. MVCC introduces additional challenges such as table and index load. I agree with all these points, right? So I agree with all these points that these happen when you have MVCC, but uh, to point out that MVCC is the reason why they have a specific failure is wrong. Now, what do I mean by that, right? So I've seen this problem multiple times in multiple places. This happens when you use a specific database for a specific workload for which it was not designed, or you have or you don't understand how the internals of your database operates, right? When a query updates a tuple or even a single field, an entire row is copied to create a new version. This is done in almost all databases. If you take the case of Mongo, take the case of Postgres, take the case of Elasticsearch. Now they do it in a different way. Things may be done in different ways, but in order to ensure that concurrent accesses of data are do not cause inconsistencies in while reading the data. This is a very important feature actually, right? Because if you don't have this, you get into this place where you are reading inconsistent data. So which means that if you have a transaction or if you have multiple concurrent transactions happening at the same time, you may be susceptible to partial reads, right? And that's definitely not the case that you want your database to experience. Uh, so I think this is more of an anti-pattern on how Postgres is being used, and they need to look at append-only databases, and they need to modify the queries to understand that this is how it should be. You cannot use Postgres as in how you seem fit, and just say that it's not that MVCC is an issue, right? This is more of and yes, I do agree with this with the points where it leads to write amplification. These are all known points about Postgres, and we do need to and we do need to be aware of this. And I'm not saying that this can always be avoided. No, this can happen, and but it cannot happen very frequently. It cannot, if it's a, you have to identify, you have to understand why it's happening, and you have to change your patterns. Awesome. Moving on. By the way, hats off to Professor Andy Pavlo. If you are a database nerd like me, I would suggest you go to YouTube, find out videos by him. It's awesome. Great. Moving on. Okay. So scaling PostgreSQL to millions of QPS. To mitigate these limitations and reduce drive pressure, we continue to migrate shardable. Awesome. Okay, so this is one of the solutions for ensuring that your databases don't have a single property which could fail under heavy write traffic. Right, heavy workloads to sharded systems that is Azure Cosmos DB. I do understand why they are using this. I don't understand why this could not have been done in their existing cluster, right? You take the case of there's so many take the case of Bytes. For MySQL, there's, I think PlanetScale is also doing something. There are so many instances of companies who built their own sharded databases, and they basically have a shardable layer which ensure it kind of plays very well with the application logic. And yeah, I mean, I think you don't have to use Azure Cosmos DB to kind of support a shardable workload for your system. But I think we'll get to that point later. I understand what they did there. What they did here, it must have been easier for them to kind of move certain workloads onto Azure Cosmos DB. Sure, but again, I don't see why they could not do it with their current setup. We also no longer allow adding new tables to the current Postgres deployment. Uh, this sucks for the developers at OpenAI. Um, okay, I don't think I need to say anything further for this, right? You don't allow. I mean, yeah, I don't think I need to say anything about this. New workloads default. Okay. So what they mean is, for the existing database Postgres deployment, it's a they don't allow adding new tables, so they want to move new workloads to the sharded systems. Sorry, I take back my statement. This is a completely fair requirement. So for some reason, they were unable to have a sharded workload. They were unable to build a sharded workload layer for their Postgres deployment, so they move to Azure Cosmos DB, and in order to ensure that the teams don't keep on adding new tables because it's more familiar to use the existing Postgres cluster. They ensure that no new tables can be created. Cool. Even as our infrastructure has evolved, Postgres has remained unsharded with a single primary instance. The primary rationale is that sharding existing application workloads would be highly complex and time-consuming. Okay, I don't agree with this, because if you are saying that you can no longer add new tables, so what if you need to add logic to your existing to few existing application which has the table which has logic in the Postgres deployment? So you are you saying that you want to fetch data from multiple Postgres or multiple DBs to answer those queries? I don't think that's less complex. Okay, requiring changes to hundreds of application endpoints and potentially taking months or even years. Again, it depends on the mess of the code base that they have in OpenAI. It seems I don't think this is fair. I don't think this is a fair statement. I think having a system where they have Postgres and Azure Cosmos DB is a bigger pain. Now, what they may be planning is that they may be planning to move the Postgres deployment, the data in the Postgres instances over to Azure Cosmos DB. That makes sense, but again, I don't agree with this, because I think more or less the complexity would be the same, right? And I also talk about how you can go about doing this, on the fly, dynamically. How do you basically fix this entire system to operate that way? Since our workloads are primarily read heavy and we've implemented extensive optimizations, the current architecture still provides ample headroom to support continued traffic growth. Cool. I think now they dive into the challenges we face and the extensive optimizations we implemented to address them and prevent future outages. Awesome. Okay, moving on. So the first section is reducing load on the primary. Sure, with only one writer, single primary setup cannot scale writes. Agreed. Heavy write spikes can quickly overload the primary and impact services like ChatGPT and our API. Again, depends on the kind of workload, the right workload that they have. We minimize load on the primary as much as possible, both read and writes, to ensure it has sufficient capacity. Okay. Read traffic is offloaded to replicas wherever possible. However, some read queries must remain on the primary because they are part of the write transactions. This is an important point, right? So people assume that you can, in order to improve your read traffic percentage, that they can just keep on adding more read replicas, and that you can handle scale that way. The problem with that is, depending on the kind of application that you have, you offer certain guarantees to your user. And when you are reading data from a read replica, there is always going to be some kind of lag. Now, the lag may be in milliseconds, the lag may be in seconds. For traffic that for the traffic that OpenAI has, right? It can also be in minutes. It can also, I don't think it can be in hours because that's a complete failure otherwise, right? But it can also be in minutes. So that means that the moment you write to your system, and if you do a read, let's forget about a transaction, right? So let's say you write to a system, and the next time you read from your read replica, you may get outdated data. You may get stale data, and that read may have other serious consequences for your application, right? Uh, and that is how, and if this was a financial system, it may have a lot of other complications, unless and until they have restrictions in the application or the client logic, right? Not when I say client, I mean the backend logic, which kind of interacts with the DB. If unless and until they have some security measures implemented there, then it may be okay. But otherwise, just assuming that you have a primary and you're writing to a single instance and you're reading from multiple instances that everything is hunky dory. No, you may kind of get into very niche problems. And when you get into those problems, I mean, they can be quite devastating as well. For those, we focus on ensuring they're efficient and avoid slow queries. Uh, okay, I don't know how they're doing this, right? Because if they can ensure that you can avoid slow queries, then do it for your entirety of traffic, right? That's the solution. For right traffic, we have migrated shardable, heavy workloads to Cosmos DB. Again, no problem there. I just don't know why their current system could not have been adapted to do that, to workloads that are harder to shard but still generate high volume, take long to migrate. I think the problem here that they are not bringing out is that their workloads may be in the wrong place. The workload that they have, or maybe is not suitable for Postgres, and I think that is something that they have not yet talked about in this blog till now. We also aggressively optimize our applications to reduce write load. Again, I don't know if so. You're saying that it was easy to optimize applications to reduce write load, but it was not, easy to fix it properly. So that's dual talk, and I don't understand that unless I have more context. For example, we fix application bugs that cause redundant writes. This is a bug, right? And introduce lazy writes where appropriate. So you mean that you had certain traffic which did not need to write data synchronously, right? And you can write data slowly. So again, this is an application problem. This is not a database problem, to be honest. To smooth traffic spikes. In addition, when backfilling table fields, we enforce strict rate limits to prevent excessive write pressure. Backfilling table fields. This is one of the most common problems that you'll find in a lot of applications, right? So, and if you are someone from the web app world, right? So I think you may have heard of something called migrations. So oftentimes we write migrations to, create tables, to create a data layer schema. But you also write migrations to write data to a specific column because you want to backfill it. And when your database grows, or when your app grows and your database kind of grows along with it, right? And let's say you have millions of rows in your database, backfilling table fields will always be very expensive, and it has the highest potential to take down your uh, database instance. Uh, Now there are multiple well-proven ways to remedy that. There are ghost migrations. There are other so whatever they're doing, right? So you can also do it lazily so that you don't have to take down the database. You don't have to. So there are multiple ways of doing it. But again, I'm just saying that this is a very common problem that most apps have to solve in some way or the other. Okay, so yeah, so we covered how just having read replicas does not mean that you can increase your database performance, infinitely and for each query as well. You have to be conscious of the trade-offs you're taking when you are using read replicas compared to the primary instance where the write happened. Okay, moving on. So we have query optimization here. I think this is a few expensive queries such as joining these many tables together. Okay. This is something which is very application specific. We can discuss if this is the way it should have been done, or do they just need to do something else here? For example, we once identified an extremely costly query that joined 12 tables with spikes in this query were responsible for past high severity SERPs. So again, right? So why do you need to join 12 tables? What kind of so does it so there may be a problem with the overall view, with the API, with how the data is being stored. So again, I cannot make this I cannot comment on whether this can be avoided or not avoided based on what they are doing. But yeah, so this is very specific to their application. Again, okay, this is a very meaty topic for me. We should avoid complex multi-table joins where possible. If joins are necessary, we learn to consider breaking down the query and move complex join. Yeah, this is fair. This is what I would have done as well, and this is what the application does allow you to do. Many of these problematic queries are generated by ORMs, object relational mapping frameworks, ORM, so it is important to carefully review the SQL they produce and ensure it behaves as expected. Now, this is a problem that I have with the topic on ORMs, right? So many people in the database world believe that ORMs are the main cause of problems for everything. Now, what ORMs does is it does, represent your specific database object in a more object-oriented format, which kind of makes it easier for you to query things in accordance with your with the language that you have picked. It also, simplifies a lot of other things that you would anyways have to do, right? And it ensures that it gives you a proper interface, which can save you against different kind of security attacks as well. So there are lots of pros to using ORMs. So now what? So but what? When people say that ORMs are bad, so they usually talk about the n+1 query problem, right? And what the n+1 query problem is that when you have to fetch an object and that object is connected to a different table and so on. Let's say that you have a chain of objects that are connected to each other. So you to fetch one object, you have to do more calls, right? You have to do that many calls. So if you have to fetch n objects in the first table, that means you would have to do that many calls in a sequential manner as well, continuously for the entire object, right? Now, the problem with this kind of thinking is that it's not like SQL saves you from doing these kind of operations, right? It's just that ORM makes it very simple to do this, and I think this kind of problem you could get into if you don't have any awareness of how your query is performing or how you are querying your tables. So the fundamental problem here is not with the ORM, it's with the developer. It's with your layout of your entire data. So ORMs are not at fault here. So my counter argument to those people who say that ORMs are bad, my counter argument is that does SQL prevent you from making these kind of mistakes? If no, then ORM is not at fault here. ORM does make it so even in ORMs, right? It's not like you cannot. So, for example, let's take the n plus one query problem again, right? Is it very difficult to solve this via ORM? No, you have eager loading, you have preloading, you have so many different kinds of optimizations that are already available to you, and maybe that are already available to developers when they are developing, right? So you don't have to use plain SQL ever. So just use a ORM, but be aware of what's happening in your application. Second of all, n plus one query problem. Come on, man. These are very simple problems that most that it's very easy to identify. For example, let's take the case of this where they are joining 12 tables. You are saying object dot one dot load dot object dot two dot load dot object dot. So there's some kind of chaining which is happening because of which you are doing these kind of queries, right? It's are you saying that this could not have been caught in a code review, or are you so and if this could and if this could not have been caught in a code review, that means your developers may not have been aware that this kind of problems may arise, or maybe it was an oversight because you were smaller when someone wrote the code, and now that you have kind of grown to a certain extent, now you cannot afford these kind of mistakes. But to put the blame solely on ORMs, I do not agree with that at all. Are ORMs the best way to kind of write SQL queries? I'm not saying they are. There are other ways, other more better compiled or generated ways of kind of writing SQL queries, which does which you can, for example, you have SQLC in Go, right? I think that's one of the best ways to use the power of both the ORM and also ensure that you gain all the safety checks that comes by default when you use an ORM, right? So yeah, so that's one point that I wanted to kind of talk about, because it's a very common notion across most developers nowadays. Cool. So we move on to the next part where they talk about the single point of failure mitigation. I think we covered this in the beginning itself that if you have just a single Postgres instance or primary instance which is taking care of all the write traffic, then you are definitely going to be affected if that specific node goes down, or even if the overall load of write traffic is so high that your single Postgres instance is not able to keep up with it. I think in this paragraph, what they're talking about is let's go over it. Most critical requests only involve read queries. I don't agree. But okay, so this is application specific. To mitigate a single point of failure, the primary we offloaded those reads from write to replicas. We've already covered these. While write operations would still fail, the impact is reduced. It's no longer a safe zero since reads remain available. Um, Again, no comment on this because I don't know exactly what reads they're talking or what writes or reads or they're talking about. From my perspective, failing to ensure that a write request is properly persisted is a safe zero incident as well. But yeah, I mean, they clearly don't, think that way. So yeah. To mitigate primary failures, we run the primary in high availability mode, of course. So I think what this means is that they have a primary replica and they also have a secondary replica, which is all the time kind of again reading the replication log from your Postgres instance, so that the moment your primary node goes down, or if your primary node is not available, then a secondary node kind of kicks in, and it takes over for the write request, and that is how you can ensure that even if something happens, or if your primary node needs to be taken down for offline maintenance, you still have a secondary node that can kind of come in, become the primary, and still handle the write request. Is this a foolproof solution for all the write traffic? No, this is a temporary bandage, and this is also something which they're doing to maintain high availability, right? But that does not mean that. But there are cases when your systems, a single Postgres instance will not be able to handle as much load, regardless of whatever health the system is in. So those kind of situations, I don't think they're they're planning on handling this. This is fine. I mean, there may be a data center failure in a specific region, so they can just move over to some other instance in some other region. Again, we need to I need to understand more about how they have configured their high availability configuration. For example, when a write comes, so now there are two modes of replication, right? So the first mode is when you write to a specific uh, instance, right? Let's say you have two Postgres instances. So you have the primary and then you have the secondary. Is you write to the primary instance. Now there are two options that you have that you could do here. For the first option is that you write to a Postgres instance and you don't return back an ACK until and unless the write also goes to the secondary instance as well. So that means you have to write to multiple instances at the same go. Maybe sequentially, maybe not sequentially, but I think it has to be sequential, because what if fails in the primary cluster and it succeeds in a secondary instance, right? Sorry, primary instance and then it succeeds in the secondary instance. That's a terrible failure as well. So I don't think we could do that. So that's one of the options, right? Where you basically return a successful response only when the writes are successful on both the nodes. The other way to do it is where you always write to your primary instance and you immediately return back a successful acknowledgement to your client or to a user. And in the backend, you kind of replicate data to your secondary node. Now, the problem with this approach is that what happens if you have already returned a successful response to the user and then your primary node goes down before the data is replicated to your secondary node? This is a very classic problem that is common in a lot of the distributed systems that I've worked in. So you need to guard against these as well. So I'm pretty sure Postgres has a config which allows you to do the go for the first case. Even for the first case, there are cases when you can do parallel writes both to primary and secondary instance. And then if something happens to the primary node where it is unable to do an acknowledgement, there are other cases, there are other checkpointing mechanisms that you could kind of potentially do to kind of ensure that you are fast, but you still don't lose your consistency guarantees. So yeah, so I think this is okay. Nothing out of the ordinary. Moving on, workload isolation. We often encounter situations where certain requests consume a disproportionate amount of resources on Postgres instances. Okay, for example, a new feature launch can introduce inefficient queries. Again, I don't think you should wait to have a feature launch in production to kind of identify inefficient queries. I think this is a clear shortcoming that the OpenAI team has to address pretty soon. You should have proper staging and QA environments and proper test suites as well, or load testing suites where you can identify these kind of inefficient queries before they even go into production. And a lot of big tech companies do actually have these kind of restrictions or guardrails around their applications where they kind of restrict you from doing a lot of funky stuff, which ensures that these kind of issues are well caught even before they get into the master branch. To mitigate the noisy neighbor problem, we isolate workloads onto dedicated instances to ensure that certain spikes in resource-intensive requests don't impact other traffic. Okay. So this is something interesting. Specifically, we split requests into low priority and high priority tiers and route them into separate instances. So when they say they split requests into low priority and high priority tiers, right? That means unless Postgres has a way of, or some other extension has some way of doing this, they need to have a middleware or a proxy layer which sits in between the user and the Postgres servers, which kind of can identify certain requests as low priority and certain requests as high priority, right? And then what they must have been doing is that for high priority, they must have a specific set of read replicas, and for a low priority tiers, they have a specific set of read replicas. So based on that, they kind of uh, they kind of redirect them onto the correct read replicas. I think the problem there is that you have to categorize each traffic as based on priority. And most of the times, what I've seen is, how do you assign something as low priority, right? For example, let's say I want to say that my notification is a low priority traffic. Fair. I mean, from first glance, maybe it is, right? Because I don't need to be notified immediately. But what if it's a critical notification? What if it's a payment failure notification? I need to know about it immediately, right? So you go into the rabbit hole where it's difficult to identify what kind of requests are important and what kind of requests aren't important, right? And so I think how this will pan out is that they will kind of, even in these priority tiers, they'll basically start assigning more static tiers like medium, high, critical, all these different types of tiers that they will start defining. And once they understand that, okay, this does not work, that it's very static in nature, and it's not very configuration friendly, what they will do is that they will start dynamically, assigning a specific score to your traffic, and then based on that traffic, or the pattern of the traffic, they will route them to different tiers. So ultimately, that is what you would have to do. But yeah, I think that is too out of the that's not something that they could do right now, because I guess it also requires a pretty intimate knowledge of the entire application as well, which the database team would maybe is kind of ramping up on. Okay, moving on, we go into connection pooling. Each instance has the maximum connection limit 5,000 in Postgres. It's easy to run up connections. Okay. We have previously had incident caused by connection storms that exhausted all available connections. We deployed PG Bouncer as a proxy layer. I think PG Bouncer, I mean, if you have ever deployed Postgres by itself, PG Bouncer is a must-have tool. I mean, I don't think I have seen any production Postgres deployment without PG Bouncer. Um, that's also because of how Postgres treats connections. For example, in Postgres, every connection is a separate thread or process, which kind of makes it very expensive to have these many concurrent open connections. So having PG Bouncer allows you to pool database connections, so you don't need to have as many database connections as concurrent requests. So yeah, I think this is a no-brainer. But this is also a pretty standard thing that they already have. So let's look at the diagram. They have user request, goes into Kubernetes service, it goes into a Kubernetes deployment. Yeah, they have PG Bouncer pods. I wonder if uh, I think I need to investigate more on this, but I wonder if PG Bouncer is stateless or stateful. Depending on that, it will depend on what kind of Kubernetes deployment they are doing. Maybe I have a different video about this later on. Each read replica has its own Kubernetes deployment following multiple PG Bouncer pods. We run multiple Kubernetes deployments. Sure, this makes sense. Pretty standard stuff. Cool. Caching. A sudden spike in cache misses can trigger a surge of reads to solution to reduce. Okay, using caching layer to serve most of the one cache read reads from unexpectedly. Yeah, I think this is a pretty common problem, but it's also because they are treating the cache as something which is always going to be there, which is actually not the case. Cache systems are, it's always supposed to be temporary, unless and until and they are supposed to be very well dimension. I mean, you know what kind of requests you want to cache and what you don't want to cache. So I think in this case, it's more of cache everything, which is why these kind of hit rates drop, right? But yeah, again, a very standard problem. Scaling read replicas. Yeah, this is interesting. Just a sec. In the beginning, I was talking about how Postgres uses write ahead logs to kind of write data into its own disk, and then different instances of Postgres, be it the read replicas or the secondary instance, they kind of read from the they kind of read from the WAL, the write ahead log of the primary instance, and they kind of insert the same data into their own instance, and that is how these read replicas keep themselves up to date. The primary must ship while to more instances. Yes, this is a very classic problem. So what this means is so as the number of replicas increase, the cost and the network bandwidth to ship to move the WAL to more instances kind of keeps on increasing. With increasing the network. Yeah, this is a very classic problem as well. This causes higher and more unstable replica lag, which makes the system harder to scale reliably. We operate nearly 50 read replicas across multiple geographic regions. Okay. And this is a key point that we should remember, and I'll come back to it again in the future. But yeah, however we can architecture the primary must stream WL replica. Okay, we can't keep adding read replicas indefinitely without eventually overloading the primary. To address this, we are collaborating on cascading replication, where intermediate replicas relay WL to downstream replicas. Yes, so I have actually seen a lot of incidents around this cascading replication, and so it's also called replication chaining in certain other databases. So what this means is that in the beginning I was saying how your primary writes data to the write ahead log, and your secondary replica and your secondary instances and your read replicas basically pull data from the primary node, and they kind of update their own disk as well with the data that they fetch from the primary, right? So that's what I was saying. So now what cascading replication means is that you have a primary instance. So it means that your read replicas don't have to listen only to the primary instance to insert data into their own disks. They can also listen to the write ahead log of any other read replica as well. So I think the only condition is that you need to listen to a read replica which has a op time. And when I say op time, it's basically the operation time or the write ahead log time. Basically, it's the unique identifier that is based on a timestamp. And what it denotes is my log, do I have more logs than you or not? Basically, I mean, is my timestamp of a log greater than the timestamp of your current log or not? That's what it means. So how it works is that your read replica may talk to another read replica, ask the read replica what is your current uptime, and if your uptime is higher than mine, then I can just get data from that read replica and update my own disk as well. So that basically means that now all your nodes in your cluster, all your read replicas don't have to talk to only the primary, right? They can talk to any of the read replicas, and I would have to check how Postgres does it, but I guess you could have a static mapping of which nodes you want your read replicas to listen to, or you can also make it dynamic, I guess, where a lot of the read replicas, they basically share heartbeats amongst each other with the uptime, and then your read replicas can decide, okay, this is the node that I want to talk to, right? That's a perfectly fair problem, but the problem with this approach is that your replication lag, it does help the primary to kind of reduce its overall network bandwidth, and the and IOPS and other resource consumption as well. But it does mean that your replication lag it increases even further. For example, let's assume that it takes 100 milliseconds for your read replica A to read from the primary instance. Now, if there was a read replica B who wants to listen to the write ahead log of read replica B, and then there's 100 milliseconds there as well. So that means that that your read replica B is 200 milliseconds behind your primary instance. And if you start chaining this, let's say to 10 nodes, then it means at one point of time, a specific read replica may also be an entire second behind your primary instance. Now, let's take the case of where they talk about, I think I think somewhere they talk about multi-region deployment, right? So in multi-region deployment, the latency is even higher. So and again, 100 milliseconds may also be quite low compared to the volume that they are sending, right? If you just increase the latency to 500 milliseconds between each node, then a replication node can go up to 5 seconds as well, which is, which can cause a lot of headache for your entire system. So that's a very that's one of the issues of having cascading replication or using replication chaining. There's another problem that you would see, right? Uh, and this is to do with how rollbacks happen. So how rollbacks happen is, let's say you have so I'll not go into a lot more detail here, but when rollbacks happen, you basically have you compare your compare your write ahead log with the primary's write ahead log, and then you may have to move back a few of the you basically revert back some of the writes that you had done before to get to the same state as the primary log. But so when you enable the cascading replication config, it means that rolling back is going to be even more difficult, because there may be multiple bifurcations of your write ahead log based on different replica states. So if at certain point of time you had a primary which then became a secondary. Sorry for that. So what I was saying, that if you have a primary which became a secondary, but you and at a single point of time, if there are the primary is transitioning to your secondary and the secondary is transitioning to primary, but your read replicas are basically pulling data from multiple instances. So your overall the main source where you are fetching data from, when it kind of changes or bifurcates, it's very difficult to kind of get back to the same state, or basically to revert back to the proper state when your rollback or something like that happens. So it can also lead to cascading failures and cascading rollback. So that's one thing that we should remember. Yes, so here we have a diagram where you have primary, you have there's an intermediate replica which is reading from the write ahead log, and then you have multiple read replicas which are reading from these read replicas, and then you can also have other read replicas. You can have another layer of read replicas as well. So I don't, so that's okay. Rate limit, again, perfectly fine. Yes, so this is in a nutshell what I think of the entire OpenAI's blog post on how they are scaling Postgres. There are lots of things that can be improved, but I think it's a good start with pretty standard stuff on how to scale your databases. Hope you had fun listening to this video. Thank you so much, and see you again.